Hello, I'm Dr. Michael Greaves, and welcome to my presentation entitled Digital Twins in the Third Millennium Discontinuity, From Physical Trial and Error to Goal-Directed Navigation. My premise with digital twins is that human existence is about being goal-oriented and using replication of reality, predicting how the future will unfold, and then navigating to our goals past the obstacles that arise. To discuss digital twins in the third millennium discontinuity in this context, I'd like to start off by taking a step back and discuss where we are in the arc of human history. I think it will emphasize how unique the era that we live in is. The first millennium, starting in 0 AD, was for the most part a continuation of the millennia that had existed before as civilization. Our energy sources were primarily human and animal, with some use of natural resources such as wind and water power. Communications between humans basically took place with language, in person, or if written by hand, at the speed that a human or ship could travel. The only computing power was in human brains. But the world was pretty simple, with the main goal being survival. So human brains were usually up to the task of replication, prediction, and navigation using trial and error. The second millennium, starting in 1001, is a discontinuity from a physical standpoint with the previous millennia. It literally starts off with a bang, as gunpowder is invented in China in the first century. This opened the idea that there was much more powerful energy sources available to humans. But the world stayed fairly simple for centuries. Energy sources and communications methods were the same. The printing press in the 1400s made dissemination of material from one to many much more efficient in disseminating knowledge. But that was one of the few major technological advances. However, the last few centuries of the second millennium produced tremendous advances in sources of energy, from steam to fossil fuels to electricity to the ultimate energy source, unlocking the atom. Communications follow suit with the ability to communicate with radio waves, over wires with telephone and telegraph, and then instantaneous worldwide communications via satellites. Human brains, with some assist from electronic calculating devices, remained as the only source of computing. However, the world became complex, outstripping the abilities of humans to replicate, predict, and navigate. Inefficient trial and error to obtain goals was still dominant, though. This brings us to the third millennium, which began in 2001 and is marked by a discontinuity in virtual computing capability. The first few years, we have digital twins, IoT, three-dimensional models, metaverses, and a wealth of other technologies moving us into the virtual world. Computing capability has advanced tremendously, such that in 50 years, supercomputers have gone from megaflops to exaflops. That's a trillion times increase. The third millennium is the first era in which prediction itself can be computationally augmented. We can now replicate reality digitally, predict large numbers of possible futures, and navigate toward desired goals before acting in the physical world. The major discontinuity is not that we can build more powerful computers, it is that we can increasingly move work from the physical world into the virtual world. The human brain has been augmented dramatically by the rise of artificial intelligence. It is in this world we are making quantum leaps and being more effective and efficient by using this virtual discontinuity. The third millennium is the first period in history in which computation can systematically augment human predictive capability through continuously replicated digital realities and large-scale prediction of future possibilities. We are replacing inefficient trial and error with computing predictive capabilities. These predictions enable the generation of information, which is the selection of candidate actions together with the evidence-informed estimates of their probability of successfully navigating toward defined goals while minimizing wasted physical resources. So to summarize, in the first and second millennia, we had goals that we attempted to accomplish. We replicated the physical world the best that we could with our senses. We then engaged in trial and error actions to obtain those goals. We wasted resources at a tremendous rate until we got something that was close to achieving our goal. In the third millennium, we are in a completely different position. We have our goals. We can replicate the physical world not only with our senses, but with instrumentation. We can then engage in our computing capability to predict future states as to what's going to happen. We can also predict that if there are any anomalies that will prevent us from obtaining our goals, that we can predict which actions will best put us on a path to obtain those goals. We can then navigate to our goals by executing those actions to obtain these goals. We are using our computing capabilities to use data and information rather than trial and error to obtain our goals as effectively and efficiently as possible. I will be describing how we are doing this with what I've been calling front-runner simulation, or FRS. I would like to first share with you the original digital twin model that I introduced over 20-some years ago. It was the conceptual ideal for product lifecycle management, which was this new idea of moving from a central functional-centric perspective to a product-centric perspective, and it had the name information mirroring. It didn't get its name digital twin until later in that decade when my colleague at NASA came up with what I felt was a much better name with it. But pay attention to the model. It's going to come back in my later part of this presentation. This is the digital twin model that you'll see most often today. It has three major components. It has physical objects in a physical environment. It has digital or virtual objects in a digital virtual environment. And it has data that we get from the physical world and use it in our digital arena. And then we use the data and information that's developed there back in the physical world. And so it has these three components, the physical, the virtual, and a persistent connection between them. I use this model because, as they often say, a picture is worth 1,000 words, but word definitions really don't do digital twins justice. In fact, I've got a paper that down there below that got released fairly recently that we went through 358 definitions, and they all differed pretty wildly from each other. In fact, fully a third of them were not really describing digital twins. And because digital twins are very complex, as I showed you, the scale and scope is pretty broad. And depending on what they're being used for, they will have different definitions. So I would contend that the idea of a visual model makes a lot more sense. Why do we want to do this? Well, because in the 20th century and before, as soon as we had some idea about a product, it had to take physical form. It had to be written down, drawn, a physical prototype. We are moving our work into the virtual digital world in the 21st century, or as I like to call it, the third millennium. And so this digital twin is really a product of our capabilities that we've never really had before. And so this kind of a model is going to drive productivity, effectivity, and efficiency in the 21st century. So the model that I just showed you has the major components that give you a really good idea about what digital twins are all about. But if we're going to actually kind of work with them, I am back to my original model because I think it better describes what are all the capabilities of a working digital twin has. And the first kind of capability is the fact that while I have physical space and digital space, I need to have the digital space populated by models of reality. As I have said, is that the digital space needs to act exactly like the physical space does in terms of having the laws of physics and of the universe and how it operates. It's not a video game. You need to have a fidelity with the physical space so that when you predict, you're going to predict basically using the laws that our physical space operates under. We in our physical space have this idea of the digital twin objects, the people that operate them, and the environment that's around them. The initial digital twin only worried about physical objects, but in essence, if we have the physical space, we want to have basically the environment that it operates in, because that has an impact on the physical objects, what the weather is, what the forces are operating on it. We're going to take data from the physical world and populate the digital space with it, and then we're going to use information and data from our digital space in order to basically do work, because doing work with bits is much, much cheaper than doing work with atoms. It gets cheaper with bits, gets more expensive with atoms. We are going to then to populate our digital space with the physical objects that we're dealing with and the environment that they operate in. We're also going to, in essence, let the subvirtual spaces inherit what is replicated over in the big box in the physical space, so that simulations start all off at the same time. We may vary, and we will vary, in essence, the assumptions that we use about predictions, but basically what we need to do is to have these virtual spaces inherit what exactly is happening in our physical space. What we have that we haven't had before is the ability of having artificial intelligence whose natural habitat is in digital space. And so we, in essence, want to have my little friend there, who I call artificial, populate that. And so this works whether we're talking about humans in the loop or humans not in the loop. And this really helps in terms of understanding the digital space with their digital metaverses and how they're going to operate. So from the original slide of the digital twin, it was to be the premise that it underlied product lifecycle management, which is the indication that we move from a functional centric to a product centric perspective, as indicated by the little diagram there, is that I divide the product lifecycle into 4 simple areas. We create the product, we build the product, we operate and sustain the product, and we dispose of the product. So digital twins were meant to indicate that we were taking a product-centric perspective. There are 3 types of digital twins that we can use. The first is what I call the digital twin prototype. And you can tell from the pictures there that it starts off as a fuzzy idea and it ends as a fully blown engineered product, and also with the means of production, because if you engineer something and you can't manufacture it, it doesn't do you any good. And so the premise here is that the digital twin really starts before the physical twin, and it comes about when I'm going to actually create a specific product. I'm not fooling around with designs. I'm going to physically make a product, and it will have digital twins. These are all the products that can be made, because it's both the engineering, it's the manufacturing. In fact, we like to test the product. We like to also operate the product in digital space, because it's much cheaper to do that than it is to move around physical atoms. When I start to make products, I basically am looking at the fact that I now have individual products. I don't have tolerance for my manufacturing, or I don't have simply the fact that it has radar. I have specific serial numbers, and I have specific measurements of that product. So each product I made is going to have its own individual twin, what I call a digital twin instance. And that digital twin instance is going to basically be maintained, connected to its physical product, and represent its physical product throughout its entire life. So these are all the products that have been made. But one of the real powers of digital twins is I now have a population of products that I can collect the data on how they're operating. And it's what I call the digital twin aggregate. And I can use that, in essence, to do Bayesian-based predictions about how products have performed in order to understand how products will perform in the future. So the digital twin aggregate is the idea that these are all the products that have been made, and in essence, I want to capture their performance so that I can basically be able to predict what individual instances are going to do, at least on a Bayesian probability basis. So what we're going to do with this computing capability is what I call front-running simulation, that basically employs digital twins and AI to, in essence, help us look into the future to understand what problems we're going to have to address and address them before they happen, or mitigate them so that they don't affect us meeting our goals. And so this is still the digital twin, but it's done now in a horizontal fashion, where the physical world is on the bottom and the virtual world is on the top. And so the first thing we obviously do is, at time X, we have the physical world as it exists with our digital twin objects. And so what we do first is we need to replicate what that physical world is, the states of that physical world, and capture that in our digital twin environment. But then what we need to do, and what we want to do, is use our little crystal ball there to, in essence, predict what possibly could happen. There are various things in terms of the prediction that could happen, and we need to, in essence, look at what are the possibilities. What happens in the physical world is all those predictions basically resolve into something that actually happens, but at this point in time, we're looking to see what could happen and looking at the probabilities of, for example, adverse events occurring that we are going to need to deal with that will stop us from reaching our goals. So here's the whole outcome of digital twins and AI front-running simulation. As I showed at time X, we basically have something that happens in our physical world, and we capture that by replicating, using data to replicate that in our digital twin environment. So we capture both the objects and the environment. So we basically have the state of our physical universe in terms of what's happening in the physical world is replicated in the digital virtual world. While I showed you having multiple predictions, only one thing is going to actually happen, and in essence, this is the threshold that we figure out that there will be a deviation that will occur that we're predicting. And so the question now is, what do we do about that in order to stop it from affecting us meeting our goals? And so in terms of predicting, we use both forward prediction with causal predictions. So we basically have the laws of physics that we employ, but we also, as I talked about previously, have Bayesian-based predictions from our digital twin aggregate that basically tells us what has happened in the past where we've had this kind of condition that we're replicating, what's actually happened when it's gone out in time and actually something has occurred. So we use basically this hybrid version of both predicting from simulation and, in essence, calculating the probabilities of what will happen, what has happened when we basically have these sort of situations. What we want to do is we want to look at our ability to have different scenarios of what can happen if we take certain actions that we want in order to either avoid the deviation or to mitigate it. In some cases, stopping the deviation may be more expensive than doing something later, allowing the deviation to occur, and in essence mitigating them. If we have to take a machine down in a factory that basically stops the line, that's very expensive. So there may be other options to prevent bad things like bottlenecks from happening later on. So we're going to look at that kind of probabilities of what will happen in the future under various conditions. Because what we want to do is we want to come up with what I say is information, which is how do we replace wasted resources? And in essence, we're going to use that information that we select from the strategy that we picked out here in order to be able to what I call navigating. Navigating is successfully getting to my goal, and so this basically having a deviation and then having this information allows me to say, if we do this sort of thing, I predict that we will meet our goal. But the key is we actually have to replicate that in the physical world, and so the execution of our strategy for, in essence, avoiding the deviation is extremely important. And so this is an entire condition of front-running simulation. I just had a paper that's come out talking about that if you're interested in more specifics. But this is digital twins with AI front-running simulation that basically is why we want digital twins and why we need data that we can use in order to do replicating, predicting, and navigating. This figure summarizes the substrate or conceptual framework behind front-running simulation, or FRS, and shows how data is transformed into actual decisions. Across the top are 4 foundational elements. Models of reality represent our understanding of how the world works. They guide what data we collect and how we interpret it. Data provides a continuously updated replication of the current state of the physical world. Simulation combines those models with the data to explore possible future states. Finally, information is not simply processed data. It is a selection of actions that best navigate toward defined goals while minimizing wasted, scarce physical resources. The center of the figure emphasizes that simulation is the integration engine. It brings together 2 complementary forms of prediction. Causal simulation, driven by models of reality, explains what would happen if, based on cause and effects relationships. Correlative simulation, driven by historical and real-time data, estimates what is likely to happen based on statistical patterns. Individually, each has strengths and limitations. Together, they provide more robust foresight than either approach alone. At the bottom is the front-running simulation process itself. The first stage is replicate, where a live digital representation of the physical system is continuously maintained. The second step is predict, where many possible future states are evaluated using both causal and correlative methods. The final state is navigate, where those predicted futures are converted into actions that maximize the probability of achieving system goals while minimizing the expenditure of scarce physical resources. The key message of this figure is that digital twins are not simply about creating virtual spaces. Their true value lies in transforming continuously replicated reality into informed actions that enable organizations to proactively navigate to their system objectives rather than merely reacting after events occur. We tend to gloss over or take for granted models of reality when we talk about digital twins. We tend to simply assume that they exist in our digital twin metaverses or environments. However, predicting and navigating requires that we have programmed our universe's models of reality into our virtual one. Simply put, models of reality are simplified, testable representation of how the world works. Humans learn by experience early and intellect later. Humans start to learn these models of reality immediately after birth. Babies almost immediately learn the permanence of objects. If an object is placed in front of them, it just doesn't disappear. Human children continue to learn from experience, such that if a stove is hot, it will burn. We then learn some of the more non-obvious, complicated models of reality later in life through intellect and education. Einstein's theory of relativity was hardly obvious. However, GPS systems would not exist if we didn't understand that theory. While models of reality are given in our physical world, we must program them into our digital twin metaverses. While we can replicate without models of reality, prediction and navigation accuracy is reliant on having models of reality in our digital twin metaverses. So digital twins are driven by data. As the chapter that I have listed is the data-driven digital twins, describes the role of data. The reality of it is really we don't have data scarcity. The universe basically presents us with an infinite amount of data on a constant basis. But what we do have scarcity of is data that we can capture and use, and determining how to do that is extremely important. So data are facts about reality. I mean, if we want to replicate the physical world, we've got to know what makes up the states of the physical world and be able to select and capture it. So we have to basically look at data that are selected for a purpose. So what data are we going to capture? What purpose are we going to use it for? So we want to make sure we're capturing the data that we have use for. Otherwise, we're basically having massive amounts of data, but it will do us no good. We'll have no information. It needs to be contextually relevant, meaning that the data has to not only simply be a string of numbers, but it has to reflect what's relevant about the context that it's in, the environment that it's operating in. So we select data that basically reflects that. It has to be objective. So previously to IoT and, in fact, censoring in general, is that data was always human mediated, meaning people collected the data, and whether you could rely on it or not would depend on how well that they could define what was objective. We've now moved into a world where we now can capture with instruments, and we have much more reliability about what the data is that we're dealing with, because it is always constant no matter who's collecting it, because it's being collected by instrumentation that follows the rules of physics. It needs to be complete. So we need to have all the data about the phenomenon we're looking at. An example I've used is the fact that if a machine is susceptible to vibration, which causes its failure, and we're not collecting vibration information, we're really never going to predict the failure of that equipment. So we have to have a complete set of data that basically will allow us to replicate and predict the future. It has to be accurate, so it can't vary from collection to collection, because if that happens, then we really don't have a good feel. If these are facts about reality, we need to collect reality that basically we can say, this is what actually occurred. And finally, it needs to be interoperable. We need to be able to take the different data that we have, and this is where the issue of data scarcity comes in, is if we don't have interoperable data, we don't have data that we can use. And I will talk about interoperability as a key here in just a second. I discussed earlier that the value of digital twins in all digital transformations is to move work from the physical world into the digital virtual world. This is the idea that information is a substitute for task-wasted time, energy, and material. Almost all of human existence in our physical world is what we do is we goal seek while we try to minimize scarce physical resources. We live in a physically constrained world, and therefore what we need to do when we are doing our task is to try to minimize our scarce resources. The bar on the left-hand side here realizes that particular concept, in that I can take any task that I want to perform, whether it's designing a quality product, or building and manufacturing a quality product, or even using a quality product. I can divide that task into two parts. The green bar is the minimum amount of physical resources that we would use for completing a task if we were omniscient or omnipotent. Everything above that is what I call information inefficiencies, or in essence, to be simpler about it, wasted physical resources. We can cost those resources as time, energy, and material, and be able to put a cost on what it takes us, in essence, to design a product, to manufacture that product, and then to support and operate that product. Our intent here is we would like to use the minimum amount of physical resources that we possibly could in order to be able to do that task. In fact, in manufacturing, we call that lean manufacturing. Our intent is to be as lean as we possibly can so that we're not wasting physical resources, and that we are, in essence, being able to do things as efficiently and effectively as we possibly can. Where information comes in is the fact that information replaces not the physical resources that I need to do my goal-seeking task, but for the red wasted resources. Except for the yellow contingency on the right-hand side, the blue section here shows the information is replacing all inefficiencies or wasted resources. But in our human endeavors, that usually is not possible. This is reflected in the use of the yellow contingency resources I've added recently. If our probability of execution is higher, but wastes more incremental resources, we may choose to do that action versus the most efficient action that we possibly can, because we cannot, in essence, rely on the fact that we can execute that efficiently. The other advantage here with information is what I call a non-rival resource. Over on the left side, when I use physical resources, and in fact, when I waste physical resources, I basically cannot reuse those resources again. On the right-hand side, with information, when I use information to replace wasted physical resources, I don't use up that information. I can use it over and over again. So there's a huge opportunity here. Now, the issue is that we don't have a unit of measure for information resources, but we can actually get there with a proxy of hardware, software, and humans' time. Information is not free. It costs something to develop it, store it, and process it. But once we do that, it can, in essence, be used over and over again without using information up. Where does this make sense to do? It makes sense to do when the cost of information for all the times that I'm going to do the task is going to be less than the cost of wasting time, energy, and material. If I have a one-time task, it doesn't make sense for me to create an information system or develop an information system to, in essence, replace the wasted resources. I will simply use trial and error. But if I'm going to do this task over and over again, and I'm doing similar tasks, then this information can help me replace wasted resources of time, energy, and material over and over again. Time, especially elapsed time, is our most scarce human resource. We cannot recover the time of a clock that elapses and ticks away. This is the idea behind digital twins, digital transformation, and why we're seeing such a pressure to move our work from the trial and error physical world into the much more cost-effective virtual world. This figure illustrates how artificial intelligence, or AI, extends front-running simulation by combining traditional physics-based simulation with data-driven AI prediction to create a more powerful decision-making capability. At the top is the current replicated reality, the live digital twin instance that continuously reflects the current state of the physical system. From this common representation, two complementary prediction paths operate in parallel. On the left is white box simulation. This is the traditional engineering approach that uses physics-based and causal models to predict how the system should behave. It is transparent and explainable, allowing us to understand the mechanisms behind the predictions and to explore what would happen if different actions are taken. On the right is black box AI, which draws on the experience of the digital twin aggregate, or DTA. Rather than relying on explicit physical models, AI analyzes large amounts of historical and longitudinal data to identify patterns and make Bayesian evidence-based predictions about what is most likely to occur, even when the underlying causal mechanisms are not fully understood. The center of this diagram is where the two approaches come together in hybrid prediction fusion. When the physics-based simulation and AI predictions agree, our confidence in the predicted outcomes increases. When they disagree, that disagreement becomes valuable information, prompting us to refine our models, investigate anomalies, or collect additional data. The panel on the right highlights another important role of AI, Rather than simply predicting outcomes, AI can generate prior probability distributions that rank the most likely future possibilities. This focuses simulation effort on the most probable regions of the solution space, making front-running simulation both faster and more computational efficient. Finally, the fused predictions drive navigation and action, supporting risk-aware decisions, execution of the selected actions, and continuous monitoring and adaptation. The key message here is that AI does not replace physics-based simulation. Instead, it augments it, combining causal understanding with statistical learning to produce stronger, faster, and more reliable decision support. I stated the need for digital twin interoperability earlier. FRS is a systems approach which will require multiple digital twins in a metaverse environment. Physical world atoms enforce what I have called cohesion. Cohesion is a capability that binds digital representations together so they behave as a single integrated system. This is analogous to how physical laws bind components together in the real world and requires interoperability. The example I always use is if I lengthen a steel beam in the physical world, I also increase its weight. So how can we obtain this cohesion and interoperability of digital twins? The first approach is ad hoc programming. We control the interoperability of digital twins because we control all the programming. This is the brute force method. We cannot control all the programming and we'll have digital twins from multiple sources. Another approach is to develop standards. Ontologies, attributes, method called semantics. The problem with standards in the digital world is that they would be bit-based, and we would have to have very exhaustive standards. In the physical world, atoms and molecules implement standards. In the digital world, we have to specify each individual bit placement, which is highly problematic. Having exhaustive standards, I contend, is not really feasible. We can have harmonization. We can get a group of people together and decide what the digital twins are going to be made up of and how they are going to interface with each other. That does work if you have a small enough group. However, getting groups to agree takes time and effort. We can have middleware. Middleware companies will basically say, if you're using this kind of digital twin or that kind of digital twin, we will do the mapping so that they interoperate. We can have digital twin platforms. Companies will offer a platform for specific purposes, say nuclear reactor digital twins. That will basically specify, here's how you have to program your digital twins. Finally, I think we could use AI agents. Agentic AI would be able to get us digital twin interoperability. This is my view of the use of agentic AI for interoperability. We would have agentic AI in digital twin metaverses. These AIs would be the interface between different digital twins. AI would explore the different digital twins and translate and map their interface connections. Agentic AI would provide interoperability and enforce cohesion. As a system and system of systems approach to goal achievement, FRS requires digital twin interoperability. I'm strongly encouraging research into an agentic AI approach as a solution here. Here is my list of selected publications that is out on my ResearchGate site. The last paper on the list is my just published paper on front-running simulation that will explain in more detail what I have presented here. I also have my YouTube channel listed at the bottom. Thank you for your attention today, and I know you'll have a fruitful and enjoyable rest of your conference.